All right, hello everybody, and welcome back from the break. We're going to start session 8 now. My name is Gina DeBraccio, and I am one of the chairs along with Rachel Philwett, and she will be moderating the discussion. This is working group 4, connecting activity across the heliosphere. And we're going to start, if you're following the agenda, with 4 talks, and that will lead into the I'm actually going to wait to address any questions until the end of all of the talks, and then we'll get into a big discussion there. So let's jump in with our first speaker. We have Olivier Witos, who will be talking about tracking an interplanetary coronal mass ejection through the solar system. Take it away, Olivier.
Okay, good. Do you hear me and do you see my screen?
It looks good and we can hear you.
Okay, so thank you very much. So good morning, good afternoon. Thanks for the invitation. So I was asked to present the study that we have done with many colleagues about this October 2014 CME that was tracked by 9 probes in total, and we published the result in JGR a few years ago. So in fact, everybody started with the encounter between Mars and the Siding Spring comet that happened in October 2014. So we are very interested to understand the relationships between the coma of the comet and the Mars atmosphere. So when we started to analyze the data with the Mars Express teams, we were very confused because it was not easy to find immediate sign of the interaction between Mars and the atmosphere of the comet. So in fact, the team were confused because the data indicated more like a space weather event or solar wind disturbances in the data. So we were quite confused, and we tried to identify whether a space weather event took place more or less at the same time of the comet encounter. So that's how this whole story started. So we looked at the location of planet in the solar system, and we find that there was an interesting alignment between the Sun, Mars, and Comet 67P with Rosetta doing some measurement at the beginning of its nominal mission. So if there was a solar wind disturbance at Mars, we may find some interesting information in the Rosetta data. And given the timing of the event at Mars on the 17, 19 of October, if there is something at Rosetta, it will be around 22, 23rd of October 2014. So we looked at the data. So that's the Rosetta data. Fortunately, the spacecraft was fully equipped with plasma and field sensors. So you have, as a function of time, so you see from the 22nd to the end of October, here we have the 3 components of the magnetic field. We have the total magnetic field. That's the radiation data, the radiation monitor of Rosetta, and that's a zoom on the magnetic field, the radiation data, and here the solar wind speed. And indeed, we find a clear signature of ICME. If you see the solar wind speed here, the jump on the 22nd of October, we had a clear jump in the magnetic field data. So that's the quiet solar wind, and then you see the large jump. And in addition, we find this strong decrease in the radiation data, which is the indication of the passage of the CME called Far-Bush decrease, but it was mentioned during this conference already. So we are quite happy to identify the event at Rosetta. So based on that, we say, oh, we should be able to find the CME candidate from solar data. So we contacted solar expert because we are not solar expert ourselves. So we looked at the Proba2, SOHO, and Solar Dynamic Observatory data, and we find a good candidate of a CME ejected from the Sun on the 14th of October at 2014 at 1830. You see the parameters here, 850 kilometers per second, and the CME was the large one. So based on this information, once we know about the source of the disturbance, we looked again at the Mars data. So we know the departure of the CME. We know what's going on at the Comet 67P. So let's look at Mars data. And we were fortunate because at Mars, we had the Maven orbiter, which just arrived a few weeks before. So that was great. We have the Mars Express data, we have the Mars Odyssey data, and we have even the rover data from the Mars Surface Laboratory equipped with the radiation monitoring. So different panels, so that's the Mars Express data that I was showing before. So solar wind density and solar wind speed with the clear disturbance here in particular in the solar wind speed. We had the neutron monitor data from Mars Odyssey, which indicate the Far-Bush decrease associated with the CME. We see a similar Forbush decrease from the surface of Mars, from the Mars MSL radiation monitor. We find also the indication of the CME in the magnetic field data from MAVEN, even if it's more complicated because of the crystal magnetic field at Mars. But nevertheless, we had a clear signature of the ICME on the 17th of October. So that answered the question that the event of the encounter of the comet was disturbed by the passage of the ICME. So that was more or less the end of the story. And we are quite happy to have this clear identification that helped to understand what's going on with the comet. We even got help from Leila to run some dedicated run of the Enlil model to understand the propagation of the ICME. So I think we had a very clear picture of the event that helped, in fact, understanding what's going on at Mars and at Rosetta. So that was more or less the end of the story. But when we looked at again the position of different planets, we find that Saturn, given the large size of the ICME, Saturn must have been hit. So we had a look at the Cassini data, and with the help of the Leicester colleague, we find the signature of the ICME from the Cassini data. We were again quite fortunate because Cassini was in the solar wind at that time. So we find this identification of the passage of the ICME in the magnetic field data. So the total magnetic field here and the three components here. And again, looking at the high energetic particle sensors, we find the Forbush decrease associated again with the ICME. So, and we checked again with Leila that the timing of the ICME with the Enlil model also was relatively okay. I mean, at Saturn, it was with an uncertainty of 2 to 3 days, which I think was okay to consider at this distance. So again, maybe we thought it was the end of the story, but we continued to look at other data because New Horizon was again in the cone of this ICME. So let's look at New Horizon, which was en route to Pluto. It was a few months before the Pluto encounter. We looked at the data. Here it was more complicated because the first to identify ICMEs at 30 astronomical units, it's not easy, because it's always difficult to predict what happened at this large distance from the sun. So with the help of Heather Elliott, we looked at the SWAP data to try to find the identification of the ICME, even more complicated without any magnetometer on board. So we looked at the SWAP data, so a spectrometer to look at possible signature. So that was not easy. From the speed of the solar wind, we find a few possible signs of solar wind disturbance. The clearest sign was this low density region, which could be associated with the over-expanding area. And given the timing, given the previous points, or at the comet Saturn and the speed of the solar wind, we also identified a window of the arrival, which was at the end of January 2015, in line more or less with the solar wind Enlil simulations. Still not the end of the story, because Voyager 2 was also in the cone of this ICME. We looked at the data and we find a possible identification here in the dynamic pressure data, and again the GCR data, which indicate a possible Forbush decrease. At this distance, we were very cautious not to claim any clear identification, but at least that was the possibility that we documented in the study. So we, based on that, we had the clear timing of the ICME by 9 different spacecraft. So we were quite satisfied with the study. We were able to derive the change in the ICME speed as a function of distance, and for different portion of the ICME, so the western flank, the eastern flank, and the middle of the CME, that we compare with the Enlil simulations, and that gave a reasonable match, where you can see the sudden drop of the ICME speed within 3 AU, and then slowly the speed going down to the solar wind ambient speed. So I think that was quite interesting, because we managed to find different spacecraft data for the same solar wind event. But then after that, we decided to check, because we don't have always a spacecraft with plasma data available at the time of the solar wind disturbances. Or sometimes we have a spacecraft with no particle data. So we are thinking to use engineering data like the bit error that is recorded in spacecraft memory or spacecraft computer. Some of this engineering data could be sensitive to solar wind events, and if we manage to find out there is a clear relationship between those data and solar wind disturbance, we could use many spacecraft to track solar wind event in all the solar system. So we are at the moment trying to identification of space weather event based on that. So you see an example here. In September 2017, there was a very intense solar winds event at Mars, so ICME with a
less
SEP.
than 1 minute.
Yeah. It's almost my last slide.
Perfect.
And so that was the event recorded by Mars orbiter. And in black here, we have the bit error of Mars Express computer, which see a clear relationship between the solar winds event. So we are working on that. So if we are successful, hopefully we can use many more data sets in the future. And this is my last slide. So some concluding remarks. So first, for the analysis of upper atmospheric data, I think it's very important to always consider the space weather context, which is not always done by planetary colleagues. Multi-mission, multi-instrument, multi-target is always a must that confirm the event, and you can get different angles to a different event. We use the expertise of many different scientists, so planetary scientists, instrument scientists, modelers, solar and solar wind experts, which is always good, fruitful. And the spacecraft housekeeping data, they are very promising for space weather studies. So that's my last slide. Thank you for your attention.
Wonderful. Thank you so much, Olivier. We'll be holding questions for the discussion section. So we're going to move right on to our next speaker. We have Layla Mays, and she will be talking about heliospheric modeling opportunities at the Community Coordinated Modeling Center. Layla, you can share your screen and unmute.
Okay, I'm going to go ahead and start sharing. All right, is that working?
Looks good. And then you can put it into presenter mode.
Oh, yes, of course. Okay, yes. So you've introduced the title, and the Solar Heliospheric Modeling team at CCMC is myself, Peter McNeese, and Sandro Tektekishvili. This is a chart showing you all the different models we have at CCMC. So it actually spans a lot of domains, all of the heliophysics domains. And I'll be focusing on the solar heliosphere models, but basically some of the models that you can use for some of the WHPI research and what new things we've done. So a little bit more focus on what's new. Okay, so CCMC offers a service called Runs on Request that many of you may be familiar with, but if not, I did want to mention that you basically go to our website. We have computing clusters and storage, and you basically log in and you fill out a web form, and then we execute your run, and you receive a web page with the results, and you can do some online visualization, or you can download the results if you need everything. So yeah, we've been around since 2001, and we receive model deliveries from the community, often an outcome of their grants. We also do runs in real time. We call these continuous real-time runs, and we host most of these outputs on the ISWA system, which the URL is listed there. And basically any model that we can run in real time, we run it in real time to test it out, see how it's working. And really it helps see how the model does in a sort of, quasi-operational setting, provides feedback to the model developer, and often a lot of the people here may know it can offer science campaign support. All right, so just to give you some updates on some models that you can use that are new, we have the Corhell Mass TDM model. So that's from the Predictive Science group. So this is the Titov Demilon Flux Rope Designer that you can use. It's available on the CCMC website now. You can click on the links that I have there to get to that. And you basically design your flux rope, and then you can submit the run on our website and evaluate how that CME erupts or doesn't erupt. And then from there, you can do more advanced simulations. So this is a very recent development, one of the first flux rope models that we've been able to offer. And we are planning to upgrade this model soon. Another one is the SWMF Awesome model, and that one is from University of Michigan. We've offered, this is the first one we offered that offers a magnetic flux rope, but this is a Gibson low flux rope. There's a tool that you go to called Eagle that allows you to design your flux rope again. It's a little bit simpler, and then you're basically running the solar coronal and heliosphere part of the simulation with SWMF Awesome R via CCMC. And you can also create these synthetic chronograph images as an option. We also have an upgrade to WSA, and for the first time, we're offering it on runs on request. In the past, it wasn't really necessary, but now users can do a lot more things with it. On the left is a screenshot from ISWA, so that's the real-time run, and we've created a new gallery signet, so you can look at different locations, different input maps. And then very soon, we're going to have this neat probability contour graphic that will show you the solar wind sources based on a bunch of different WSA runs. We also have the time-dependent WSA NLIL available, and it's the available version is version 2.8. So you can see it's kind of a time-dependent heliosphere evolution on the right. On the left, that's actually a bunch of different adapt realizations that you could use to drive your simulation. Another new development is SEPMOD, so that's coupled with NLIL. So that's an SEP model, a particle tracing model. And this is an example of that model coupled with NLIL. It's basically taking the shock information along the observer field line and then producing the intensity profiles anywhere in the heliosphere. That's available in real time and runs on request right now. This is just a chart because we are moving more into SEP models. We're going to start to onboard some more, showing you how there are more coupled heliosphere and SEP models in the community. And some of them will be offered via CCMC. Particularly, we're looking at onboarding. We're in the process of onboarding IPATH and MFLAMPA and also EPRIM. All right, so we also post a lot of our real-time model runs on the scoreboards, and on the scoreboards, the community can post their real-time results. So that's a little bit different than just looking at our outputs. And I'm not going to go into detail on the scoreboards because there isn't much time, but I did want to highlight the SEP scoreboard. This is just a screenshot of that because it's now publicly available, and those links are listed down there. And the new SEP models that are available in real time are Release, UMSEP, SEPSTR, SEPSTR2D, and then I mentioned SEPMOD before, which is the only kind of MHD physics-based one, and MAG4, which is a probabilistic forecast. And this is just an example of a screenshot of what the scoreboard looked like for a recent SEP event. But this is available online, so you can take a look and feel free to ask questions. I did also want to advertise the COSPAR iSpot teams because CCMC is heavily involved in these. One of the roles of CCMC, in addition to serving simulations, is to provide model validation. And a lot of these teams have, there's at least one team in each of these clusters that has a validation activity that CCMC is involved in. And then finally, I wanted to post this link to solicit a little bit of feedback. This is a project kind of bigger than CCMC. The heliophysics digital resource libraries at Goddard are interested in hosting heliophysics data on the cloud for people to use on the cloud, as opposed to downloading it, to your laptop. But they want to get an idea of what data is would be the most valuable. So if you click on that link, there's a link to a survey, or you can get in touch with me with some of your ideas and thoughts. And yeah, so I just wanted to mention, we are also looking at other models. We're probably going to receive a core HAL upgrade soon. We're also in touch with the Gamera team at WHPI. So hopefully in the next year, we'll get the solar helio and geospace model. I didn't list that here, but that one is also being onboarded. An upgrade to NLIL. IPath and SWMF-M FLAMPA, that's the SEP model, and EPREM. And that's it.
All right, thank you so much, Layla. Please stick around for the discussion, and that's where we'll talk about all the questions that come up for you. We'll move on to our next speaker, who will be Jacob Grusbeck, and Jacob will be talking about a generalized magnetospheric disturbance index utilizing an artificial neural network to scale to large mission data sets. Jacob, you can take it away.
Great, thank you. Let me bring the screen up. Okay, it's yeah, my camera doesn't seem to want to be starting, so I will just, in the interest of time, skip that. Okay, so yeah, as Gina already mentioned what the topic is going to be, but more specifically, we're going to talk about our initial application of this neural network method to MAVEN observations. So for those of you who aren't around the MAVEN mission a lot, one of the primary mission goals of the spacecraft was to address the atmospheric loss of the Martian atmosphere, and more specifically, its loss to space from various solar drivers, and most specifically for our study, space weather events. Previously, a lot of case studies have been done where folks have modeled atmospheric loss. They've looked at the outflowing ions, but this has been a case-by-case basis. So picking particular CMEs and then looking at the response to the system. A lot of these then tended to use qualitative descriptions. They said, we looked at this and it was a strong CME or a big CME, but there wasn't any sort of the statistical or quantitative descriptions that we might use at Earth, where we have an abundance of different disturbance index. So that said, Mars is, we use the word hybrid magnetosphere because, as we've discussed, as Christina mentioned earlier today, there is no global intrinsic magnetosphere, but Mars does have a bunch of crustal magnetospheres. So it is really a complicated magnetic environment, and it causes a pretty unique problem. To say something about how disturbed a magnetosphere is, you also have to sort of say, what does a quiet period look like? And at Mars, that baseline is constantly moving. It's dependent on how the IMF is draping around the planet, what direction it's draping around, what sort of interactions with the crustal fields. One orbit is never quite the same as the next orbit. So to do this, we've developed a first attempt at a magnetospheric disturbance index, and we're doing this all by time. And to get around this problem of the baseline moving, we end up normalizing how disturbed the system looks by what does it look like before the event hit the planet. So far, what the work that we've submitted and is in review is been done by hand, and that's pretty time consuming. So later on, we'll talk about how we've started using machine learning to transition this to a more mission-wide data set. Here's a typical, this is a example of MAVEN's observations of a CME. This was the March 8th, 2015 ICME. So this was one of the major CMEs that we studied after MAVEN arrived at the planet. I'm only showing a small snippet of the plasma observations from the spacecraft, but the top panel, we show the solar energetic particle observation. And here we can see that at the very far left side of the plot into March 7th, we see the really high energy SEPs hitting the planet, and the slower SEPs start to come closer to when the ICME actually impacts it, midday to late on March 8th. The middle panel is the solar wind ion analyzer, and here is just a pretty blatant. It looks very obvious when the shock hits the planet and the disturbance washes over. And final panel here is the magnetometer observation, and this is the one that we're focused on for this disturbance index. And the two values that we look at the most are first this increase of the amplitude as the CME hits the planet, the whole baseline amplitude of the magnetic field rises. Additionally, the variability inside the magnetosphere increases. So it becomes more turbulent. There's more waves been excited as the transient is washing over. So we use the two magnetic field observations, the amplitude and the variability, and then we normalize it for normalize it by a baseline, which is the average of the day before the event hit. That gives us this MIDI that which we call which is our attempt at giving this sort of disturbance index. Here we plot that same March 8th, 2015 ICME, and we see the initial hit of the shock here mid to late on March 8th, which is about 35 hours from the start of the time period we used, a quick rise up, and then we see the decreasing of it. What's interesting in this plot is this particular ICME was actually the third in a series of 3 ICMEs. So we actually are seeing a little bit of a hint of that earlier ICME that impacted the planet on March 5th still there. In red, we put a Gaussian fit onto the MIDI because we were curious about the length of time the planet stayed disturbed. So it was an initial attempt at quantifying that, how long was it disturbed. We took a Gaussian and then we were able to calculate full width half maxes to kind of give a metric for the disturbance time. We did this for over 70 events. All of these were picked by hand. So on the left-hand side here, we just put all 70 events, superimpose them on top of each other with the maximum MIDI at 0. In dash blue and dash red are 2 ICMEs that have been published pretty consistently on, the March 8th one and the stronger September 2017 ICME. I also mentioned here this highlight a green and purple one, mostly because these were ones that we didn't publish a lot on, but they're outliers in our MIDI event database. So it's already highlighting events that maybe we missed, maybe that overlooked, or just because other research was happening. Next, we were curious is there, with that duration that we calculated from the full width half max, as well as the maximum disturbance index, was there any correlation to the disturbance power versus time, or the type of disturbance even? So on the left hand of side, the right plot in the middle panel here is just the scatter plot, which kind of shows that there is no real correlation between duration of the event or the strength of the event as far as this MIDI number is concerned, nor is there much of a correlation of the type of event. Everything is just kind of randomly distributed in this panel. One thing that does show is that a majority of these events are pretty short-lived, and essentially the length of time of the transient being at the planet. So what this tells us is that the planet quickly comes back down as after the transient has passed over the planet. So that was great. We did these 70 events by hand, and it takes a lot of time. So what we envisioned with this isn't so much picking out an event, looking in the past where we already knew an event happened, but was more of a mission-wide data set as a way to look at what's happening at the planet and alert us if something interesting had happened. Because we can't do this manually every time new data comes in, it just becomes too expensive with human time. We started to work on using a computer to help us with this. And to do that, we started to develop an artificial neural network. One of the biggest time crunch in this method is we have to identify the region the spacecraft is in. MAVEN's orbit is in the solar wind. It brings it below the bow shock into the magnetosheath. It takes it into the ionosphere, the Martian planet. So we really just need to know where is the spacecraft in relation to what plasma it's looking at. On the left-hand side is kind of these notional plots we see in a lot of artificial neural networks of what does our network look like. We have one layer, which is all the data that gets fed in. So we're feeding our network the position of the spacecraft, magnetometer observations, and the solar wind electron observations. These data get fed into what are called long short-term memory layers. And essentially they're looking for patterns in the time series. They take in 30 time steps of data and say, does this look like something I have learned? Does this look like something I've seen before? these short-term memory modules then feed into a dense layer. Essentially, this is just a yes/no layer. It says, does this look like something? Does this look like the magnetosheath? Does this look like the solar wind? And then finally, all of this data, these nodes come together to give us just a 0 to 1 value of the probability that the spacecraft within the sheath.
You have 1 minute, Jacob.
Okay, so I'm gonna go pretty fast through the, we trained this on 138 days in 2015. It seems like not a lot, but it ends up being about 4 million observation points. And this is the result of that sheath prediction. And running that data from the neural network that was trained in 2015, and then we ran it on 4 years of Mars data, and we do a fairly decent job of predicting the MAVEN's position as far as Mars is concerned. As far as the bow shock is on the outer upstream here, we do a very good job. The bow shock at Mars is very variable. So in general, the fact that the neural network is saying is a little fuzzy at the bow shock is fine. It just is reading some of the variability. As far as the downtail is where we're more concerned, and we're still trying to work and get this better at predicting the downstream. I'll skip this to the punchline. We took that neural net sheath, we ran it across the entire MAVEN data set up to 2018. I shouldn't say the entire because I haven't done this in 2 years, the entire as of 2018. And we can make this, and it's the MIDI over this entire time period. And it's already plotting out periods of high activity, including that March 2015 series of ICMEs. My arrow got a little askew when I put this slide up. The arrow should be pointing more at the events here in September. So it's already doing pretty good. That said, we're trying to make it do better. We only trained it on 2015 data. We should include more days, more years, more types of solar drivers, because a neural network's only as good at predicting its stuff of what it's seen. We need to give it more time of Mars years and solar cycle. And finally, we want to repeat this process at other bodies. We're trying to keep this fairly general so we could apply it to other unmagnetized bodies. Venus is a very obvious next step. It's very similar to Mars, but that's not the only body we're looking at. We've talked about small bodies, including comets and asteroids, for example. Okay. Thank you.
All right. Thanks, Jacob. Then we'll go on to our final talk before the discussion. We have Elena Provornikova, and she will be speaking about effects of the solar cycle variations on solar wind flows in the outer heliosphere and global dynamics.
Hi, Gina. Can you hear me okay?
I can hear you, yes.
Okay, let me share screen and run slides. Okay, so I presume you have my title slide, right?
Yes.
Okay, thank you so much. And I'm going to take you further out in the heliosphere to about 100 astronomical units from the sun and talk about effects of the solar cycle variations on heliosphere boundaries and solar wind flow in the outer heliosphere. Okay, so as we discussed very extensively in this last few days, so the sun launches disturbances of various scales to the heliosphere. So there are variations of the solar wind dynamic pressure over 11-year solar cycle. There are large-scale solar wind structures, such as coronal mass ejections, and as they propagate further out to the outer heliosphere, they merge and interact with each other with the background solar wind and form into the so-called merged interaction regions or global merged interaction regions. So those are the large-scale structures that are characterized by the enhanced density, solar wind speed, and magnetic field. Also, CIRs, they evolve into the structures, periodic structures in the solar wind that were observed past 30 astronomical units, and I'll show you some of the Voyager observations of CIRs. And also, they were seen in enhancements of energetic particle intensities. Of course, there are also mesoscale structures in the solar wind, such as small-scale flux ropes and density fluctuations propagating all the way out from the sun, and even smaller scale So let me talk about some of our efforts to understand the effects of the 11-year solar cycle variations of the solar wind dynamic pressure. And these are the global heliosphere simulations that we've done in the past with the global model of the solar wind interaction with the local interstellar medium, which is developed at Boston University Group. So what we've done is that we used these boundary conditions at 1 AU that you see here. So what you see is the solar wind density on the left plot and solar wind velocity on the right. So this is as a function of time over 2 solar cycles and latitude. And these boundary conditions are obtained from observations from Lyman alpha observations and also interplanetary installations. So what the uniqueness of these boundary conditions is that we're not just that we are actually taking into account the latitudinal dependence of the solar wind. And then we ran this 3-dimensional multi-fluid model of the global heliosphere, and we looked at plasma parameters over the Voyager 2 trajectory. And so here I'm showing the results of the simulation compared with actual Voyager 2 plasma data. So in blue, this is Voyager 2 plasma observations, and in red, these are the simulations. So on the top, you're looking at the solar wind velocity, and on the bottom, the normalized number density. So from the velocity comparison, we capture the solar wind behavior pretty well. And actually, if you can see my cursor here, for the solar wind speed in the period between roughly 1996, 1999, so this is the fast solar wind that we were able to capture because we have this latitudinal dependence of the solar wind, and this is the solar minimum period. So the capturing this fast solar wind was important. And actually in the previous models that ignored the latitudinal dependence of the solar wind velocity, were not able to capture this Voyager data being in the fast solar wind. And as we go to larger distances from the sun, or well, here it's shown versus time. So we look at larger times, or corresponds to larger distances from the sun. We the model shows higher velocities than observation, and this is likely caused by the probably too low number density of interstellar neutrals coming to the heliosphere that leads to the slowdown of the solar wind. So there are some discrepancies in densities here that we see, especially during the solar minimum. In the model, we have higher density than in observations, which is probably the consequence of the boundary conditions. And so we also looked at the motions of the heliosphere boundaries. So here on the very left plot, I'm showing the solar wind dynamic pressure in a latitude corresponding to Voyager 1 and Voyager 2. So this is how the solar wind dynamic pressure changes in time, and the corresponding motions of the termination shock and heliopause along Voyager 1 and Voyager 2 directions. So the termination shock responds to the variations of the solar wind dynamic pressure in about 1 or 1.5 years. And we actually see that this deep solar minimum led to the inward motion of the termination shock, starting from about 2005 and on. So the termination shock distances that we got in our model agreed very well with actual Voyager crossings. And so for the heliopause motion, we also see the effects of the decrease solar wind dynamic pressure, the heliopause moves inward. But in general, in simulations, the heliopause stands at the distances between 140, 170 astronomical units, which is way too far compared to actual crossings of Voyager at roughly 120 astronomical units. And so one of the conclusions of this work was actually that the time-dependent effects related to the variations of the solar wind dynamic pressure were not able to explain the thin heliosheath that was observed by Voyagers, just 30 astronomical units. In the model, we had about 60 astronomical units for the heliosheath thickness. Okay, next slide. So for the rotating interaction regions in the outer heliosphere, so the CIRs are dominant structures in the heliosphere during declining phase of the solar activity, with shocks typically forming beyond a few astronomical units from the sun. Ulysses measurements show around 5 astronomical units from the sun showed that these are very long-lived structures, and there was observations showing that CIR existed over 30 solar rotations. CIRs are efficient particle accelerators in the heliosphere for both ions and electrons. And here in the middle, you see observations from Voyager 2 at 45 astronomical units, when Voyager observed sharp structures in the radial velocity of the solar wind that are likely corresponding to CIRs because the periodicity was about 27-day period. And also later, when Voyager crossed the heliosphere boundary and went into the interstellar medium, the magnetometer observations on Voyager 1 also showed the periodicity of about 28 days, which is corresponding to solar rotation. So it is possible that these fluctuations are driven by CIRs, although it's unknown. We were not able to do these large-scale simulations to actually see if these structures can be produced by CIRs starting from the sun all the way to the interstellar medium.
You have less than 1 minute.
Oh, thank you, Gina. For coronal mass ejections, also Voyager 2 observed this merged interaction region at 79 astronomical units from the sun. And Richardson et al. 2006, they were able to determine the origin of this merged interaction region, which was a CME interacting with a fast stream. And we performed simulations and looked at how this kind of structure propagates through the heliosheath region, so across the termination shock and then through the heliopause. And we found that when the pair of shocks, the forward and the reverse shock, propagate through the heliosheath, there is a lot of discontinuities and refraction waves that generate in the heliosheath and contribute to the very highly dynamic flows in the heliosheath. And I'll just quickly conclude here. So the solar minimum conditions drive inward motions of the heliosphere boundaries. Heliopause is less sensitive to solar wind variations, and displacement are smaller than of termination shock. Signatures of CIRs are observed in a distant solar wind and also beyond the heliosphere boundary in the interstellar medium. CMEs drive shocks and reflections and the discontinuities in the heliosheath. So it's still an open question how solar disturbances evolve from the sun throughout large distances out, and we need more data and we need to advance our simulations. And one of the major challenges in the simulation is to be able to track evolution of CIRs and CMEs from the sun to the heliosphere boundary with realistic boundary conditions in a global simulation. Thank you.
Thank you so much, Elena. That was very interesting. And thank you to all of our speakers. I think all of your talks really encapsulated the motivation of this working group. And so thank you very much. Okay, so we do have some questions on our Slido, and I just posted the link again in the chat. So you can continue adding questions there. I'm actually going to start out with a question that I have for you, Elena. I hope that's all right with everyone. But I also work in the CIR community, and one of these things that the CIR people are always looking at is where exactly is the best acceleration or the most efficient acceleration happening in these CIRs. And I'm aware that we can't track them all the way to the edge of the heliosphere accurately, but where do you think we can accurately track them to? Do you have any idea of that for our simulation?
So we actually simulated CIRs in a very simplified formulation. We just ran, a train of solar wind pulses, which is way far from, realistic geometry of the CIRs, that we have not tried that yet. But from observations that I looked in the literature, I always saw that the CIRs, the signatures of CIRs are always associated with enhancements of energetic particles. Yeah, this is seen in the Voyager 2 data, this is seen in the New Horizons data, and it always corresponds to the solar wind conditions from the declining phase of the solar cycle. So I think it's an open question, what you're asking. So we do see enhancements, but it's not explored fully how CIRs affect transport and acceleration of particles in the heliosphere. That's a hot question, I would say.
Yeah, wonderful. I just know that there would be so many people interested, let's say, tracking one of these CIRs, all the way from the sun out to the Voyagers and really looking at the evolution of these particle distributions and, all that we could learn from transport and acceleration there. So thank you so much. Okay, so we do have some questions in the Slido here. Let's see. Sarah, I see you have a question. If you would like to unmute yourself and ask.
Sure. I had a couple questions for, are you talking to me or a different Sarah?
Yes, I am talking. Yep.
Can you pin the question so I can see it? Let's see. I had it.
Yeah.
I can see my second one. I was going to maybe pin the first question. I can find it myself. Well, they were linked questions, right? Yeah. So my question was, first of all, you showed velocity versus different distance using these all these wonderful different observations. Did you look at anything else? Did you look at magnetic field, density, particles? Is there anything else that you were able to do a comparison like that?
Now for these studies, we were mainly interested in the timing of the CME. So we mainly looked at the speed and at the time of the different encounters, and the idea was to compare with Leila simulations, just to constrain the models and to see if we understood the data. We also compared quickly the radiation data, so the Ford-Bush decrease at Mars, Rosetta, and Cassini. So, and there is a plot I could not show during the presentation, but you can find in the paper that you can find in JGR, and you see a very interesting comparison with the 3 Ford-Bush decreases at different locations from the sun. And from that, we did not went too far, but you can clearly see the evolution and in particular the effect of the speed, because you see the slope of the Ford-Bush decrease is decreasing when you go out of the sun, so clearly linked to the speed. For the other data set, it's more complicated. For example, the magnetic field at Mars, since we are around Mars, we are, I don't want to say contaminated, but polluted a little bit by the Martian environment. It's the same for Rosetta. Rosetta was inside the coma of 67P. So it's very difficult to get clean value of the magnetic field that we can compare with modeling. But all the data set is very rich, and I have to say we did not exploit it all. So there is still a lot to do.
Excellent. And you mentioned my other question was about simulations. You said you compared it. Did you do the sort of comparison that Elena was showing, where you were comparing the predictions of the simulations to what was being observed in different places? Or
yeah, I mean, we're, as I said, mainly interested in the timing. So Leila made a lot of runs. I remember it was a very, very interesting, because the runs, I mean, they rely on the input that when you look at the solar data. So for example, the exact timing, the exact direction of the ejection, the speed. And it took some time to get a good match with all the data. So we had data at Stereo B, Mars, the Comet, Saturn, Voyager 2. Voyager 2 we did not went for the simulation, but up to New Horizon. So, but at the end, I think we got a relatively good match with the timing. I mean, plus minus a few days from time, but I think it was reasonable given the all this data set. But maybe Leila can comment more, but I think it was very interesting to work on that.
Maybe then for Leila to ask, that's very interesting. So did you also compare model predictions of densities or velocities, I guess was mainly what you were looking at?
Yeah, we did look at velocity. I think that Olivier has a plot of velocity versus distance. So we got there's points in there that are from the observations. And then we have lines that are from the simulation. Okay. But it wasn't so easy to extract that from the simulation, but Olivier was interested in it. So we did the analysis and we were able to extract that. Yeah, I think it would be hard to compare. Well, the magnetic field maybe isn't appropriate because Enlil doesn't have, it was with Enlil and that doesn't have an internal magnetic field, but the density may be possible only if the measurements were of, high enough quality to compare. But yeah, maybe we can do more in-depth comparisons for other events.
Thank you.
Yeah, so let's see. Following in that same arena, I have a question from an anonymous person here. So Leila, could you say a few words about how you've worked with various planetary missions to help with CME modeling for possible planetary encounters? And let's say, you're a novice to working with the CCMC. How does someone reach out and, get the various data products that they're hoping to get from comparing with models?
Right. Yeah, thank you for the questions. And if anybody who asked those questions wants to speak up and tell me more, that's also fine. So you can definitely browse the website and look at all the different models. There's model pages for each one, and it should list model inputs and outputs, which should help a little bit. They're maybe not as descriptive as they could be. So then the next step would be to get in touch with one of us. So myself, Peter McNeese, or Alexandro Taktakishvili, and just tell us more about what you're trying to do. And then we can advise you as to what model is appropriate to use and what makes sense. And then for the planetary encounters, like you can do historical studies like we did with Olivier and Erica and some other folks probably on the call. But we also do real-time modeling, which some people missions may use for their campaigns or just, deciding what type of measurements they want to take or pointing they want to do in real time. So it kind of depends like what your goals are for what types of models make sense to use.
Yeah, understood. Thank you. That's very helpful. Let's see. How about we go to a question for Jacob? Gina, I see you have a question for Jacob. Would you mind unmuting and asking?
Sure, absolutely. So Jacob, I was just curious if you can tell us how easy or hard it would be to essentially take that magnetospheric disturbance index that you have created, and can you create one or apply the one that you've created to a planet that has an intrinsic magnetic field, since Mars does not?
Right, yeah. So how easy it would be, it'd be pretty easy as long as we have the magnetic field observations, and we absolutely could apply it to it. One thing, and this might be something that'd be interesting with Mercury, where it's a place that hasn't had a lot of look into of making a statistical index like this. I'd be a little apprehensive at Earth because so much work has been done at Earth making very, very much more sophisticated disturbance indexes. They really pinning down at the physics that's happening that's driving substorms and the actual interactions that are occurring with the magnetosphere during these events. So it would almost be like going back in time 100 years to when they were first looking at how disturbed did things get with their magnetometers and lighthouses. That said, yeah, it would be really interesting because one of the overarching feelings for us was wanting to make kind of an apples to apples metric that we could compare to different planets. It's a little bit easier when we're talking about all of the ones with draped fields. So in some ways, the magnetic environment is being formed the same way. So we'd have to be careful when we start looking at these intrinsic magnetic fields to make sure we're not masking important physics that's happening there.
Great, thanks. So what I'm hearing is that if there are magnetometers on the surface of Mercury, that could help your study in the future as well.
Sure, yeah.
Yeah, thanks, Jacob. I actually have a follow-up to this, and my apologies if I missed it. You know, these talks go by so quick, but does the MDI work for both CMEs and CIRs? And is this list published anywhere? So like if I or someone else who's, you know, a non-MAVEN expert wanted to do some statistical analysis, that we could kind of just jump right into this list and work on that.
Yeah. So with our work that showed the 70 plus events that I showed, that is both CIRs and CMEs, and actually one time period of comet sighting spring when it interacted with Mars. So it's a whole mishmash of all of the events. As far as is there a list of those, and essentially, well, there hopefully will be, because I'm going to include the list with the paper. So it's in. But most of those events came from some work from Christina Lee. So she has some very nice event lists that she's made with some of the MAVEN SEP work. I think a majority of the events came from her list. Some came directly from the Donkey website, the CCMC's Donkey website, of me just perusing, are there events that should have hit Mars? And then I went and used those as saying, well, did Mars see the event? So a lot of those event lists are already out there. Hopefully in the future, there will be one collated list for my event list when the paper's out.
Yeah, perfect. We will all look forward to that. And Christina, I see you have your hand raised. You can unmute.
Hi, can you hear me?
Yes.
Yeah, so I can definitely help the WHPI community with accessing this, you know, the space weather event list. I have one already published in JGR that have events, MAVEN events, going from late 2014 through I think mid 2016, and I've been actively updating that list, trying to get it published. But eventually, that list will be publicly accessible, kind of like the Richardson and Kane like CME list that they have on their webpage. I hope to put something like that for MAVEN. Mars Space Weather event list at some point, but anyone can reach out to me. I can help you with that.
Yeah, that's wonderful. And I see a comment from Layla in the chat here that they'd like to include your event list to CCME's Donkey whenever you're ready. And so that's great. I mean, I'm very happy to see the collaboration and interest coming out of this working group. Let's see. Layla, we have another question here, if you're willing. So we have a question just in more general about the scoreboards that you mentioned for CCMC. Can you explain a little bit about what those entail?
Yes, so we have 4 of them now. So on the CCMC website, you can get links to them. So our first one was the CME scoreboard. And so when you click on each link, each scoreboard has some information, like an information page about it. And, you know, it has some planning. And then if you're a model developer, like if you actually have a forecast to submit, then it tells you how to get involved, get in touch with us to get involved. And if you're just browsing, it kind of gives you more information about what you're looking at. And of course, you're always welcome to get in touch with us if you want to, if you have any questions about it at all. And anyone can use the scoreboards, like it's meant to be for the heliophysics research community. But sometimes, like if you want to guess the arrival of a CME, you can do that. It doesn't have to be a model. There are many models. The flare scoreboard is more automated. There's a file where you provide the probability of a flare occurrence. The SCP scoreboard is obviously fully automated and the most complicated one. And then we're still in the planning phase for the IMFBZ scoreboard. And for all of these, we've worked with the community in terms of building them. So we have like a community leader. So Pete Riley and Matt Owens are the community leaders for IMFBZ. And hopefully in the next year, we'll try to get some kind of prototype going or a planning phase going. It kind of really depends on community interest in the initiative as to like where it goes.
Yeah, that's great. Thank you. And that is a perfect end to our time. We are at our time here. Thank you very much for attending this working group session. I found it very interesting. And working group 4 has another session tomorrow morning. We're going to be talking about specific events during WHPI. And so we hope to see you all there.
Hi, everyone. Oh, sorry.
No, go ahead,
Sarah.
Barbara. I didn't see your face. There you go. Go.
Oh, all right. Well, thank you very much. I hope you started to get. I was so impressed with just the variety of science, but also in the way that people are really creatively comparing data and models and showing data. And so tomorrow we're going to continue with this. I think there was a lot of discussion today on transients and impacts and things like that in tracing from place to place. And so tomorrow morning we're going to start with specific events observed during these campaigns. And so this will be another opportunity for us to discuss how we can trace and observe, take the advantage of the ability to map and trace from one place to the other, one location to the other. Let's see, and then tomorrow we do have our first poster session. Please attend that. We have some excellent posters and we try to give enough time for some decent interaction. And so please give the poster people enough time. And then what closes out tomorrow is our collaboration planning discussion. So I want to remind you all, as you're listening to these talks, to always keep in mind how your work connects, how you think other work should connect, and what kind of important science we should be doing. Sarah, do you have any comments?
Yeah, actually, Catherine, do you want to tell us a little bit more about the posters?
You're muted, Catherine.
Excuse me. So we will have our first poster session tomorrow. You will be in this Zoom link again, so there's no separate link. However, I did post in the chat a link to the online poster gallery. So please go ahead, if you haven't already done so, and take a look at that. It's posted on the website as well. But this will show you everyone's posters in advance, their abstracts. A few people have pre-recorded videos as well. So come prepared to chat with the presenters. So from 10:20 to 12 p.m. Mountain Daylight Time, we will be with poster presenters. So the first 30 minutes will be spent in this session here. Each poster presenter will have a 1-minute advertisement of their session. And then we'll have 70 minutes roughly where each individual poster presenter will be in a breakout room. So you can self-assign yourself and go into individual breakout rooms and have conversations with the presenters.
Awesome. I think that's it, right, Barbara?
Yeah, I think so. Thanks, everyone. Again, I want to remind everyone, you will, after this meeting, you'll receive more information. We hope that this isn't all you're doing with us. You're going to stay engaged with us and be wanting to participate and continue analysis and coordinated modeling work with us. So see you tomorrow.